Hi everyone, thanks for checking out this video. This is going to be a quick lesson on the Logistic Growth Model, which is a model that's widely used for studying population growth. It can be applied to a lot of different kinds of populations, including cells, wild animals, or even humans. In this video, I'll give a quick overview of the model, explain the variable and parameters involved, show an example plot of what the model looks like with some example parameters, and then show how to solve for the steady states of the system. Okay, let's get into it. Luckily for us, this model is pretty simple and only involves one differential equation of one variable. For this video, I just called the variable x, just to keep it simple, and this will be the variable that tracks the level of the population. There are also two constant parameters in this model. The first one is the parameter r, and this is the maximum growth rate of the population. You might also hear it called the intrinsic rate of increase, bit of a fancier term, but this basically tells us something about how quickly the population is growing. And the second constant parameter is the parameter k, which is the carrying capacity of the environment that the population is in. So this basically tells us the maximum population level that can be sustained over time for the population. So the way I like to think about this model to understand what's happening intuitively is to break up the right side into two different parts and then think about what each part is doing. So the first part is this term Rx here, and this part represents exponential growth of the population. So if we just had this term Rx on the right side and nothing else, then this would be an exponential growth model of a population that was just growing exponentially and not stopping or leveling out. But if we look at this other term, we have something interesting going on over here. So this term is 1 minus the fraction x over k, where remember x is the current level of the population and k is the carrying capacity, which is the maximum population that can be sustained. So what's going on here exactly? Well, if we think about what would happen if x is very small, meaning the population is very small, then the fraction x over k would also be very small, maybe close to 0 if x is small enough. So then the whole term 1 minus this fraction would be close to 1 minus 0, which would be close to just 1. And in that case, we'd have the whole right side of the ODE being something close to 1 times this exponential growth model, Rx. But as the population grows and x gets larger and larger and eventually starts to get close to the carrying capacity k, then we have this whole term being 1 minus a larger and larger fraction that's getting closer and closer to 1. And that's what causes the growth of the population to level off, because we have 1 minus a larger and larger fraction. So this whole term becomes a smaller and smaller number that's multiplying this exponential growth term. So we can think about this as causing the leveling off of the growth of the population as x gets closer and closer to k. Now I'll quickly show you guys an example plot I made of this model using the parameters r equals 0.1 and k equals 100 and using an initial condition of 1. And you can see, just like we talked about, that at first the growth rate starts off being close to exponential because the population is still pretty low. But then as the population gets larger and larger and closer to k, the growth starts to level out and slow down until eventually it levels out completely when the population reaches the carrying capacity, and from there it stops growing and stays at the carrying capacity level. Now I'll quickly show you guys how to solve for the steady state of this model, and this is a pretty easy one, so you can probably already guess what the steady state's going to be, but I think it's good to solve it out anyway just to get some practice. So if you guys remember, the way we find the steady state of a differential equation model is by setting all the differential equations equal to 0, because the differential equations measure the change in the system, and a steady state means that there's no change happening, so that means that the differential equations are all equal to 0. In this case, we only have one equation, so it's already pretty easy for us. We just set this equation equal to 0 and then solve for x. Now, since we have two terms multiplying each other, we can get this whole thing to be 0 by making either one of these terms equal 0. So with the first term, rx, we can make this 0 just by making x 0. So this is what we would call a trivial steady state for this system. If the population level is 0, then that's a steady state because nothing will be happening to the population. There needs needs to be at least some population for it to be growing and for anything to be happening. So we have one trivial steady state that's just 0. But there's also another steady state we can find by setting the other term 1 minus the fraction x over k to 0. So like I said, this is kind of an easy one, and you guys probably already know what the answer will be here, but I'll show you guys the algebra just to get some practice with it. So we set this term 1 minus the fraction x over k to 0. Then we just add x over k to both sides to get x over k equals 1. And then we just multiply both sides by k to get x equals k for our steady state value of x. So this is the non-trivial steady state. X equals k, which again is the carrying capacity of the population, or the maximum level that the population can sustain over time. Alright, now I also have a little homework question for you guys to test your understanding of the model. What happens if you run a simulation of this model where you start with an initial condition for x, where x is greater than k? What will happen in the simulation? And also, how do you show what will happen mathematically? And what does this mean in biological terms? I think this is a good way to test your own understanding of a math model in general, is to be able to reason about what will happen with the model under different conditions, and to be able to reason about it both mathematically and intuitively in terms of the actual system that you're trying to model. So that's a little homework question for you guys. If you think you know the answer, maybe leave a comment and then I'll tell you if you got it right or wrong. Or if anyone's really having trouble with it, just let me know and I can also just tell you the answer too. Okay, so that's all I have for today. If anyone has any questions, just let me know in the comments and I'll try to answer them. But yeah, thanks for watching and I'll see you guys next time.